Hey guys, this video is going to cover wave physics and just a brief introduction to the subdiscipline of studying physics in general. So usually we break things up into mechanics, right? And that was all the forces and kinematics and circular motion and energies and all those kinds of things that we have done. But also we have electromagnetism, which we've done a big chunk of, electrostatics and circuits, not yet magnetism. And then there's another section known as wave physics. And it's separate because the method we use to describe the way that energy and information is transferred is a slightly different model than we did with kinematics and dynamics. For example, if we wanted to describe the energy transfer of a ball rolling down the hill, we used the ideas of gravitational potential energy and then the transfer of that depleting and converting into kinetic energy. The ball actually physically moved from one place to another, and that is what we call translation. And that is where something moves from one location to another. So it actually moves from location A to location B. All right? So this is where the object actually moves. Now, wave physics is different because what we notice is that sometimes you can send energy, right, through some sort of substance or medium, right, from one place to another. Energy or information is transferred, but the particles don't necessarily move from where the energy starts to where it finishes. So it's like the ball transferring its energy to the bottom of the hill without the ball actually having to move all the way down the hill, which seems a little bit strange at first, but I have a few examples here that I think will help make sense. Just to kind of get an idea of what a wave actually is, if we can think of a wave like in this picture that we have over here. This picture of a big water wave is a disturbance, right? It's an energy disturbance that's moving through the water, right? So water molecules that, sort of are far out at sea, for example, aren't necessarily going to end up on the shore right away when the wave moves through the water, right? So the whole idea is that the energy is what is moving, right, from one place to another. So I would call a wave an energy disturbance. An energy disturbance in a medium, which is just a substance. Now we're going to expand the definition later and see if there's certain things that don't need a medium still to transfer the energy in the form of a wave. Another classic example is a rope. So let me grab a new slide and let's take a look at that. Alright, so here's this dude at the gym. He's working out, doing the ropes, and he is, as you can see if you've ever done these before, you oscillate your hand up and down, or each hand up and down, while holding on the rope, and you see that the energy transfers through the rope in the shape, actually, of what we would consider sort of a wave shape, right? Now, let's think of it this way. I have a question. Does a particle that's right here in the rope, so I'm just going to enlarge it right there, does a particle that's right there in the rope end up over here over time? Does the particle actually go from location A to location B? Hopefully you can see that it doesn't, right? We're not sending little rope molecules down through the rope. The whole thing is made of rope, and the particles are not really moving very far from each other. They are vibrating in place because all things that are made of particles are technically moving slightly unless they're at absolute zero temperature, but they're not, right? And so the energy is still moving. And so this is one of the major points about wave physics, is that the particle does not actually move necessarily from location A to location B, but still sends the energy through the medium. So if we take a look at this wave shape, there's certain ways that we can describe the wave to compare it to other waves. So let's take a look at a few different pictures and see, can you recognize what is different between the waves, each wave? Alright, so here we have red, orange, green, blue, and violet waves, and these are actually in specific colors for a reason, which we'll talk about at a later stage. But what do you notice is different about the waves? Well, if you've studied waves in math before, then you may know some of these terms. But let's see, they're repeating, right? There's a repetitive pattern. There are some high points that are all the same height in each wave, right? There are low points that are the same height in each wave. This distance right over here from crest, which is what we call the top of the wave, from crest to crest, or from trough, which is the low points of the wave, we're going to call this distance the wavelength. Now it has this name wavelength because it describes how long the wave actually is. We use the Greek letter lambda to represent the wavelength. So each of these waves is characteristically different because they each have a different wavelength. So let's try to take a look on the picture how that shows up. So the red wavelength is pretty long compared, the orange one's slightly shorter, the green one's a lot shorter, you can see right that distance. The blue one is much shorter, and then the purple is the shortest, right? So you can see the wavelength of the red one is much longer and the purple one's much shorter. So that's how we would classify waves, and we can actually give a measurement of wavelength and say this wave is this wave because it has this specific wavelength, which is important. There's also a difference here. I'm going to pull up another picture in something else about the waves that in this picture is not as evident. Alright, so here we have two different waves from an amplifier, from a stereo, as you can visualize it, and you see the louder wave and the softer wave. What's different about them? Okay, maybe you said that one is taller than the other. That could work. But we have a specific term that we use, and that is amplitude. And that is the distance from the equilibrium line to the crest or to the trough. So that's the amplitude of the wave. So you can see there the louder sound has the greater amplitude, the softer sound has the smaller amplitude, right? And so that's how we would describe that part of the wave. So far we have a few terms. The one is the wavelength, right? That's how sort of stretched out the wave is, right? Versus something that maybe looks like this. And then we have the amplitude, which is how sort of tall or short the wave is based on how far the crests or the troughs are from the equilibrium line. So it's pretty straightforward, and this video is really just to give us some examples. Now, when we look at a wave, as we get back to our original example, when we look at a wave, what we notice is that certain waves will be really tall, right? And some waves will be really short. And so think about what that means about the energy of the wave, right? How does this wave at the top compare to this wave at the bottom? If that was a wave going through the ocean, which one would be bigger? Obviously the top one. And does that wave have more energy associated with it? Could it do more damage, right? Could it push harder? And the answer is yes. And so we see that there is actually a relationship, which we will define further. There is a relationship between the energy and the amplitude of the wave. For right now, we're going to say that there really isn't a relationship for now. This is not always. There is not a relationship between energy and the wavelength of the wave. However, later on in science, in the early 20th century, Albert Einstein actually found that that is not necessarily true, that there is a relationship between the energy and the frequency of the wave. So let's take a look at one more definition of a wave, and then we will call it a day. So we looked at defining the wavelength, how spread out the wave is. And there's actually another way that might be very useful, right? Because we may not always be able to measure this distance, the wavelength distance. The wavelength is a little bit more than just the distance from crest to crest or trough to trough. It's actually the distance of one full down and up, right? One full part that will repeat after we've gotten back to the sort of the same analogous position. So that's one wavelength. Or you could draw it this way, right? As soon as you get back to the location that you started from, so both of those are the same value. They're both the same wavelength. But there's another side to this. How long it takes to do that. So let's write this in here. So here's one wavelength. Okay, I just drew the one wavelength there. One full up, one full down, right? This is our amplitude. Here's another amplitude. That's from the equilibrium line. The distance, like we've said a million times now, is this. And the time it takes for that to occur is what we call the period of the wave, uppercase T. That's how long it takes to make one complete cycle. Now, how many cycles occur can also help you describe how often the wave is oscillating. So here's 1, 2, 3, 4, 5 and a half, right? So in this, whatever time frame this is, 5.5 waves were completed. So there were 5.5 waves in however many, let's say it was in 22 seconds. Let's say that we counted something for 22 seconds and then we divided by the 5.5 waves, right? And that value that tells us how long each wave took to occur, right? So we can also describe how many waves occur in a certain amount of time, and that's what we call the frequency of the wave. So how frequent, so the frequency of the wave is how many waves, how many complete waves occur in a certain amount of time. Alright. So that term and the period are related, right? Because if 12 waves happen in 12 seconds, then each wave took 1 second to occur, right? So then you'd have the period. And so the frequency and the period are actually inverses of each other, right? So one of the frequency equals the period, and one of the period equals the frequency. Both of those statements are true. Okay, so a quick recap. A wave is an energy disturbance through some medium, right, which we'll take a much better look at soon. And we just named some parts of a wave. We said that we have this distance, the full wavelength is we use lambda to represent that. So that looks a little more like an X. The time it takes for that to happen is the period, right? We looked at the name of the high points are called crests, and the low points are called troughs. And there is a distance from the equilibrium line to the crest of the trough known as the amplitude. And then finally, if you have multiple waves occurring in a time frame, we relate that to the frequency of the wave. So guys, the reason that we've done it this way and we've looked at the anatomy of this wave is because we just are trying to get some language we can use now as we go and actually sort of explore different properties of waves. What happens when they change mediums, right? When the wave goes from one thing into another, because waves can do that, right? They can pass through things without actually moving those things. All right, hopefully this has been helpful as a quick review if you've been out, and we will discuss this soon.